Hey there, everybody. We're going to get underway. So hope your day's been a good one. This evening, we're looking to wrap up ideas from chapter 7 and extend those a little bit to chapter 8. I think people are doing a really good job within perusal, contributing to the ideas that we have there for both looking at aspects of ionization energy and then also the Born-Haber cycle. As we move on, I know for the rest of the semester, the class is going to become even a little bit more of a flipped one, where there's going to be important ideas that are shared within perusal beforehand. And then during class, I'm going to try to supplement those, answer some questions that I'm seeing, add a few more details. But I just know as the complexity of the ideas increases here, we're going to have to use both of those spaces wisely. And so I'm really impressed with what I'm seeing so far as we've moved on to ideas in chapter 7. So tonight we're going to review briefly this idea of effective nuclear charge and how it influences the size of atoms and ions. And that's so important because I think that can then be used to explain the remaining periodic properties that we find within chapter 7. So a couple of things. I want to shoot a couple of polls at you here, though, just to get your sense of a few different ideas. I'm interested on your current perspective for your learning within this class. So first of all, let me send you this one. This one says, I am frustrated. I don't feel like I can reach my goals for this class. 1 to 5, tell me your perspective on that. I know that students' perspectives evolve, as the course goes along. As you see the different course components, you get feedback based on different exams, different things along the way. So I'm just curious your current perspective on this. Okay. Next question for you. Going forward, I plan to increase the time and effort I commit to this class. There's no right answer. I'm just curious what your perspective is on this. And I'm definitely not asking this in a accusing way. I'm just trying to get a sense of how you feel, where you're at, and what might take place going forward. Now I'm going to ask something similar right here. This one says, I have good metacognition. If I sense the ideas and skills are becoming more difficult to master, then I will increase my time and effort. It's a little bit different than the previous one. You might be contributing the time within this class based on what your own metacognition is telling you. So I'm just curious if that's something that will be a factor for you going forward. Okay, I got like 2 more for you. How about this one? This one says, my procrastination is hurting my performance in this class. I think this is a little bit related perhaps to the time and effort, but I'm going to try to make the case that it's not entirely the same. Okay, one more question for you within this. This one says, I'm willing to try new strategies or resources to optimize my learning in this class. Because what I'm going to do is I'm going to look at the feedback that you just offered on those previous ones and try to think about what does optimizing mean? Because for me, optimizing, it might be using your time more wisely. It might be allocating your time a little bit differently. It might be achieving at a higher level. I think I've got some ideas that I'll be able to share in tonight's class that's in this category. Excellent. So as always, I appreciate your results that you were sharing there. Another thought, I mentioned earlier that I have a group of students that are reaching out to people in this class to set up interviews for a Tubman. I don't know what we're going to call this, the new $20 bill. And I did a poll earlier asking if you are interested. We're trying to work through the students that expressed an interest. I don't know if we'll be able to get to everybody, but I just wanted to let you know that this is in progress. We're sending out emails to people. Students are already being interviewed, so this process is going forward. If you expressed an interest previously, you don't have to do anything again. We just try to get to as many people as we can. If you expressed an interest before and we contact you and you're not interested anymore, you don't have to do anything. I just wanted to let you know that we're trying to move ahead with this. Okay, now let's start in here with some ideas from chapter 7. So first of all, I've tried to make the case that the effective nuclear charge is going to be a really important idea for us, both in chapter 7 and then going forward. Why is the idea important? Because many properties depend on the electron configuration and how strongly these outer electrons are held to the atom. We can think about it conceptually, where we consider the charge that we have in the nucleus and how that is shielded. It's akin to this analogy of the light bulb having a particular brightness, and then the frosted glass being electrons that were shielding it relative to, in this case, it said the observer. That would be the particular electron that we're thinking about. So it's this combination of a certain amount of charge that is now shielded by some electrons. And we're asking about, well, how much does that electron beyond that, how much of the charge is it actually experiencing? What is its effective nuclear charge? That's the concept. And then when we're doing calculations within this, we have our expression that the effective nuclear charge is equal to the number of protons minus a shielding factor. Number of protons, that's Z, that's easy to look up. Just look at the periodic table for the atomic number. And our simplest way to estimate the shielding is to count the core electrons, electrons that have a smaller n value, a smaller principal quantum number. We'll count those as shielding electrons. And we can calculate the effective nuclear charge for any electron. Oftentimes we think about the valence electrons on the outside, but we can calculate it for any of them. To sort of review the idea and begin to think what this means for the size, if I have this description here for hydrogen, so Z equals 1, it's got 1 proton, electron configuration is 1s1, the effective nuclear charge acting on that electron is +1. So if I were to make a simple shell picture, I could say, okay, I got +1 in the nucleus, and then the electron is in a 1s orbital. Now, if I think about lithium, so lithium's right below it on the periodic table, number 3. I can calculate the effective nuclear charge for its 1s electron and for its 2s electron. So in both cases, it's got 3 protons. If I'm thinking about that inner electron, there are no electrons with a smaller principal quantum number, so it would have a +3 charge acting on it when it's in that 1s orbital. For the 2s, it's further away, it's in a 2s orbital now, and I've got electrons that have a smaller principal quantum number, and those act as shielding. So if I were to think about what does this now mean for the resulting atom, I think that the inner electrons now are closer to the nucleus than they would have been with hydrogen. They're both found in n equals 1, but I've got 3 protons instead of 1. So I think that inner shell would be pulled in closer. I think that the 2s electron, well, that's much further away because I have a larger principal quantum number. Instead of filling in n equals 1, it's now in n equals 2. So I think this simple shell picture, sort of like what we had with our Bohr model, this can really help me make sense of what the charge, the shielding, and the distance, how they're all being represented. Now, if I were to take this same thing, what would a shell picture look like for boron? So boron here is number 5. Take a second, think about that. What do you think a shell description would look like for boron? I think you have to consider number of protons, aspects of shielding, and where the electrons are placed. If I were to bring together those features, well, boron is 1s2, 2s2, 2p1. I know it has a +5 in the nucleus, 5 protons. I've got 1s2, so I'm putting 2 electrons on that inner shell. And in my shell picture, if I'm grouping it by the n value, I've got a total of 3 on this next shell. I'm trying to show that these inner ones, they're even closer to the nucleus. Notice it's gone from this distance to closer to even closer, because there is no shielding acting on those, and I have more and more protons. I think this outer one, I have a contraction that's taking place when I compare it to the lithium. I see this contraction as I've moved across because I haven't changed the number of shielding electrons, but I have more protons there. So it's leading to a contraction as I move across from lithium to boron. Now, this description here, 1s2, 2s2, 2p1, that's not exactly the same as the shell picture here. We know that this has some things going on, some more information that a shell picture doesn't. So this evening, we might make our model a little bit more complex to begin to account for that. But at least initially, this simple picture right here is doing a really good job of describing aspects of the size when we consider the outermost electrons, and if we begin to think about the inner ones. So when we're looking at aspects of patterns for the size of atoms and ions, we saw that as we move from the top to the bottom down the periodic table, there was an increase in size because we're increasing the principal quantum number for these outer electrons. And when we were moving left to right, there was a contraction taking place because we are increasing the effective nuclear charge. These are both ideas that we looked at last time. We saw what did it mean to make the electron configuration for ions. If we are adding electrons to form negative anions or removing electrons to form cations. So that idea of adding electrons, that's called the electron affinity. We're going to talk more about that this evening. That was when we were adding electrons to make negative anions, and when we were removing them, that's called the ionization energy to form the cations. One thing we pointed last time, we've got to be careful that when we're removing the electrons to make ions, we're always going to be removing them from the higher principal quantum number. And that became relevant because we had to be careful because we had the 4s and both the 3d there present at the same time. Now, a feature with both of these for anions and cations, we noted that the anions are always larger than their neutral atoms, and the cations are always smaller. If electrons have repulsions with other electrons, if I add even more electrons to it, it's going to make the atom larger. The anion will become larger. Conversely, if I remove electrons, I'm reducing some of that electron-electron repulsion, so the cations always become smaller. And we also looked at comparisons for isoelectronic atoms, ones that had the same electron configuration, but different number of protons. When I say comparisons for isoelectronic atoms and ions are common, I am not saying they are common in the real world. I am saying they are common on exams. They are common on exams because then it allows us to say the electron configuration is the same. What is the role of the protons there, the different number of protons? So looking more closely now then at the ionization energy. So with ionization, we are removing electrons. The definition for this is we are removing an electron from an atom in its gaseous state. We are defining it that way so the atom's all by itself. It's not bonded to something else. It's not as a liquid. It's not as a solid. It's all by itself, so we can think about the energetics of it where it's only involving the removal of the electron. We don't have to do something else. Now we can remove one electron, we can remove two, we can just keep removing until we don't have any electrons there anymore. So first of all, know this description, meaning what is the notation when we're talking about the ionization energy? The symbol I1, that's referring to the first ionization, I2, the second. Typical exam question here. Which equation describes the third ionization energy for aluminum? I see aluminum listed in all different ways there. Let me send you that as a polling question. Which of these equations do you think best matches the third ionization energy for aluminum? Okay, let me share the results here. So within the dominant choice is choice B. I agree with you on that. I saw a couple people mention in the chat that they misclicked. No big deal. All right. I mean, this is not an exam, so no harm, no foul on that. Notice within this one, so I'm agreeing with the majority on here. We're looking for having removed the third electron. Notice the other ways these are set up, and they're trying to be things that you might also find as, well, that seems plausible. The different features that I see that are not correct. Well, I see this listed as a solid. No, I need it starting out as a gas and removing the electron from that. Second thought is, when we're looking at the ionization energies, for the third one, we're removing them one at a time. So right away, I don't like the idea that I'm removing all three of them. The first ionization energy is removing one, the second removes the next one, the third removes the next one after that. So that's with our description here. So in some ways with this, we want to know the definition, and then we just want to be careful with our selection for that. Now, thoughts about the ionization energy, some important ideas here. It is always endothermic. It always takes energy to remove an electron from the atom. I mean, it was stuck there initially, right? There were protons there. It was stuck there initially. It always takes energy to remove an electron. Don't fall into some thought about, well, I know sodium is oftentimes +1. It is a +1 cation, so it must want to do that for some reason. It doesn't want to do anything, okay? It's all about the energy that is involved. So yes, it often becomes a +1 cation, but it's going to be endothermic. It's going to take energy to remove that electron from the neutral atom. Second thought here, the smaller size really is a good match for that, corresponds to higher ionization energy. Smaller size means for whatever reason, that electron now is closer to the nucleus. It's more tightly held to the nucleus. There's been a contraction there. So therefore, it's more difficult to remove it. This link between smaller size and high ionization energy, it's a really good match. That's why I wanted us to explore size first. And the factors that affect the size, well, a larger effective nuclear charge is one thing. And also the principal quantum number. What shell is that electron being found in? Now, if we begin to apply this idea right here, we know that hydrogen is a very small atom. It's only got one proton, but the electron's in the 1s. Helium is my smallest neutral atom. It's only got 2 protons, but I have both of those electrons only in the 1s orbital. And sure enough, helium is the most difficult to remove the initial electron from. So this is a great match for what we see with size. And then we see that it gets easy to remove from lithium again, because we're populated a larger principal quantum number. We see then a progression as we see this contraction as we move right across towards the noble gas. How did we explain that? We explained that last time because we said we were not increasing the shielding, but we were adding more and more protons. Therefore, we had a contraction that we moved across, and that's a great match for explaining why the ionization energy goes up. Now, along that path right there, we've got a couple irregularities, but we can explain these too. When I say irregularities, I'm looking at this difference here between beryllium and boron. It takes energy to remove an electron from boron, but it's a little easier than I would have predicted. But we can explain that because we are now removing from a 2p instead of a 2s. Back in our picture, we know that the 2s and the 2p, they're not identical. The 2p is a little bit further away. That's what I would use to explain this feature here. I see another irregularity here between nitrogen and oxygen. Well, what's going on there? The orbital diagram now tells me on that. Here's the orbital diagram for oxygen and for nitrogen. Even though I have more protons for oxygen, notice I had to pair up 2 electrons within the same atomic orbital. I'm putting 2 negative charges in the same atomic orbital. That makes it a little bit easier to remove than I would have anticipated. It's a subtlety. It must not be something that dominates other part of the periodic table, but I do see it right there within that feature. So for both of these, notice what I'm doing. I'm seeing what the data is telling me, and then I'm offering an explanation. I said that sometimes within this chapter, we're going to be making predictions. Other times you'll have the result, the experimental observation, and you explain what's going on. That's what I'm seeking to do here. Let's see what else we can seek to explain. So this is looking at the successive ionization energy, removing one electron, then the next, then the next. This was in the pre-class video. What do I see? I see that it always takes more and more energy to remove the next electron, then the next, then the next. It always keeps going up because I'm removing aspects that leading to the electron-electron repulsions. We said that as we keep removing and making cations, they keep getting smaller and smaller. So that's why the ionization energy keeps going up. They keep going up, and then this is trying to say there's a large increase, though, a large disproportionate increase. That was something that was explored within the video. And so here was, for example, data showing the successive ionization energy for carbon. You could remove one, then the next, then the next, then the next, and then there was this large increase. So within this one, I see two different ideas that I want to illustrate on the successive ionization. First of all, I see that the ionization energy is increasing every step along the way because that ion is getting smaller and smaller, so it takes more energy to remove the electron. That's the first thing I see. Second, I see when the ion becomes much smaller, the ionization energy goes way up. Much smaller means I am now removing from one of those inner shell electrons. They're much closer to the nucleus, so therefore, boom, it goes way up for the energy that it takes to remove them. This is a great match for my connection between ionization energy and size. Within this one, we had where we are asked to consider the first ionization energy and the second ionization energy in a ranking amongst sodium, calcium, and sulfur. I thought the analysis that folks had within Peruzzo really insightful on this one, really helpful. Here was a comment. I think sulfur has the greatest first ionization energy. It has the same principal quantum number as sodium, but it has more protons. So it will pull its electrons closer to the nucleus. I love the description. It's talking about how the effective nuclear charge is increasing and how sulfur would be the smallest within this group. In terms of size, I think sulfur is the smallest. I think it would be most difficult to remove the electron from sulfur. Now, goes on, how about for the second? For the second ionization energy, they said, I think sodium would have the greatest ionization energy because after removing the first electron, any further ones will now be removed from that inner shell, so it will be more difficult to remove them. I like the analysis. We got to look, what electron are we talking about when we're talking about removing the second one? Here was some more on that same subject. This description here about, I think it would be the case for sodium because we saw earlier that there was this large disproportionate jump. But this comment here about, well, they weren't really sure how to think about core electrons. Let me illustrate this a little bit more. As far as the second ionization energy, these are the descriptions for what the second ionization energy would be. We're removing a second electron from the sodium cation, a calcium cation, or sulfur cation. I plugged in here what the effective nuclear charge would be. And I showed it for each of these. Notice how the effective nuclear charge goes way up for sodium because now I've changed what my shielding electrons were. I haven't changed the number of protons compared to the initial sodium, but I've changed the shielding electron. So if you ask me which of these is going to be the smallest, no doubt, it's absolutely going to be the sodium plus. Notice how my effective nuclear charge has gone way up and it's in an n=2 orbital. So I'm absolutely certain that it would be most difficult to remove from sodium plus. Now, there was this comment in here, several that were sort of in this line of thinking. They begin by saying, okay, they can sort of follow that reasoning. They hadn't really considered the idea here about how ionization energy might be related to what they viewed as stability. And they brought up this thought about what does it mean to reach an octet and where does that fit with stable? Reaching an octet and this idea of stability, I think it's something you've probably heard of before. A lot of times these patterns in this chapter are explained that way, like in high school. But we got to be really careful because that word stable, well, what do we mean by that? If I think about this, what we've been talking about, I would say energy was required to ionize that sodium. It's always endothermic. However, it takes a lot more energy to remove an electron when we're now removing from that inner shell, because it's closer to the nucleus and there's a much higher effective nuclear charge because we changed what the shielding was. To me, that's what's giving rise to stability, in the sense that it's going to be really difficult to remove more than one electron from sodium. There's nothing magical about reaching an octet, but we've reached this circumstance where that electron now is really tightly held on compared to where we were at before, for these reasons right here. It's closer to the nucleus for the one that we're thinking about, and we've got a high effective nuclear charge acting on it. Now, that was about removing an electron. Now let's spend some time about adding an electron. That's called the electron affinity. Now with electron affinity, we sort of ask a different question. Instead of saying, tell me about the atom I initially have and consider the energetics, we've got to be asking, well, where are we putting this new electron? Because that's what's involved energetically for electron affinity. We're adding a new electron to it. So here I show two different expressions. So when I say two different expressions, when we're looking at electron affinity, it is again defined where we're adding an electron to a gaseous species. Ionization was removing from a gaseous atom. Electron affinity is adding to a gaseous atom. Now, one thing to note within here, unlike ionization energy is always endothermic. It always takes energy to remove an electron. When it comes to adding an electron, it's much more variable. If you see a negative sign, if it's exothermic, that means it is favorable to add that electron. Adding that electron, if we want to say, is easy to do, it moves it to a lower potential energy. That's what happens when I see a negative sign there. If it is a positive sign, it is unfavorable to add an electron. You could make it happen, but you got to do work. You got to do something to force it on there. It ends up being at a higher potential energy. So with electron affinity, sometimes it's favorable, sometimes it's unfavorable. What might lead it to be favorable? Well, when I add the electron, if I add it to a spot close to the nucleus, that would be beneficial. If I add it to a spot that is experiencing a large effective nuclear charge, that would be beneficial. What would make it unfavorable, difficult to add an electron? What would reduce that attraction? Well, if I have to pair it up with an electron that's already in that same orbital, that's not going to be helping me. Putting a negative with a negative. These are our competing factors. Competing factors because you might have multiple variables here all in play at the same time. So when it comes to electron affinity, we're more likely to be asking for explanations rather than predictions. It's more likely for electron affinity for the result to be given, and we say, why do you think that is? Let me step through a few parts right here for this provided data and offer my explanations for what I think is going on. So first of all, if I look right here, I see that I have all of these noble gases with positive electron affinities. It means it's unfavorable to add an electron to noble gases. I see some regions where I see negative values where it's favorable to add it. Got other ones where it's unfavorable again. It doesn't have a clear trend like my ionization energy. It's far more variable. Let me see if I can give you some explanations for what's going on in the different regions. So first of all, right here for my noble gases, if I were to add an electron, where is that electron going? It must go to a higher principal quantum number, farther away from the nucleus. Why do I say it must go farther away? Because for a noble gas, it's already filled up for the quantum number that it's at. Just as an example right here, let's say I was adding an electron to helium to make a helium minus anion. Where would that have to go? The electron that I've added now would be in the 2s orbital, farther away from the nucleus. What would be the effective nuclear charge acting on that? Well, there's 2 protons. From the perspective of that electron that I've added, there's 2 shielding electrons, there is no effective nuclear charge acting on it. So if we think, why is it unfavorable to add to helium? What have we just said? We've had to put the electron farther away, and there is no net attraction on it. Why would it stick? It's not going to stick. It is unfavorable to add an electron. How about this group right here? If we're adding to beryllium, magnesium, that's another region where it's unfavorable. Because now if we think this case, we're in, like, let's say a 2s, we add another electron, where does it have to go? It has to go farther away, out to a 2p. That's why it would be unfavorable to add one there. How about this group right here for nitrogen? Notice for nitrogen, it's unfavorable, because here's the orbital diagram for nitrogen. If I have to add another electron to this, I'm going to have to put it in one of these 2p orbitals, so it's going to have to pair up with another one. That is an unfavorable factor. How about my halogens? Now with the halogens, I do have to pair it up, right? I'm going to have to add the electron to fluorine to pair it up in the same atomic orbital where one is already present. But you know, my halogens right here, they have a very high effective nuclear charge. Evidently, that makes up for the fact that I have to pair it up. That's what I mean when I say there are competing factors. For my halogens, it's always favorable to add it. So that must be explained by saying that there's a high effective nuclear charge for that electron that I am adding to it. One more aspect that I want you to be aware of here, adding a second electron, that's always unfavorable. It's always unfavorable to add a negative charge onto something that is already negative. So if I look at oxygen, for example, it's favorable to add one electron, but it's really difficult to add a second electron, because now I'm trying to put a negative charge onto a negative anion. That's why I'm saying that it's unfavorable for the second electron affinity there. Now, I noticed within here, when we went from effective nuclear charge to size of atoms, it's a really good match for ionization energy. For electron affinity, it's a really good match too, but it's a more complex circumstance for what we're seeking to explain. Now, the end of the chapter there, I'm going to look at very briefly. If it turns out that we have to revisit some of those ideas, and when I say revisit, when we get closer to a test, I'll pick up those if we need to, but I don't want to spend a lot of time on that because we usually don't have very many exam questions from that last portion right there. One thing that we find, though, what's going on within this last part of the chapter, that whole part at the start, those were looking at the properties of atoms. Effective nuclear charge, we were talking about for an atom. We looked at the size of the atom. We looked at the size when that atom became either a cation or the anion. When we were looking at ionization energy, it was for the atom. We said it was going to be in the gaseous state. Let's look at the energy for that atom when we're trying to remove an electron. For electron affinity, that's once again for an atom. It's the energy when we are adding the electron to the atom in its gaseous state all by itself. Now, what do I mean when I say atoms? I'm saying the atom just by itself. It's not bonded to other things. It's not in combination with other things. The end of the chapter right here, it's now looking at a collection of atoms. It's not looking at just a single iron atom, for example. It's looking at a piece of iron, and that's a different thing. So at the end of it, we're now looking at a collection of atoms. When we have more than one, they're bonded together, stuck together in some ways. So what we find right here, there's a table from the textbook where it's looking at different characteristics of metals. We know where metals are found on the left-hand side of the periodic table and extending over, and characteristic properties for nonmetals. Those are on the right-hand corner. We've already looked at this a little bit as far as metals and nonmetals when we were classifying them in order to think about the ones that were going to become cations and the ones that were going to become anions. If you look within the properties right here, we're going to look more later on in the semester to better understand how those are related to the structure. Now, as far as what we've seen already, let's connect it to a few different ideas. So first of all, do metals have high or low ionization energies? In general, metals have low ionization energies. We've said that metals become cations. Now, they could also be found as metallic elements, but that idea of low ionization energy, that's a good definition for a metal. If you want to say, what would be a characteristic for a metal? I'd say it's easy to remove the electrons. My cat is agreeing with that, okay? Now, next thought within here. We see hydrogen, that's classified as being a non-metal, okay? Now, we might say why. It's on that same column as the other alkalis. We know that it can become +1, but we need to think about it a little bit more carefully. As we see within this top image right here, hydrogen is being defined as a non-metal. It's not like the ones right below it. So that tells me, hydrogen, it must not be described as having a low ionization energy because it's a non-metal. Take a second right here. See if you can explain to yourself why that is so. Hydrogen is a non-metal. How is that consistent with its ionization energy? What gives rise to its ionization energy? Is the ionization energy high or low, and why? Take a second, see if you can bring those ideas together, and then I'll share my thoughts. Okay, so my thoughts here for hydrogen, let's think back of what it is. So instead of just saying, okay, it's here on the top corner of the periodic table, what do we know about hydrogen? It's got one proton, one electron found in the 1s orbital. There are no shielding electrons for that. It's only got one electron there that's experiencing the full +1 of the nucleus. And it's in a 1s orbital that is close to the nucleus. If we put together those different variables right there, it's really difficult to remove the electron from hydrogen. We saw earlier within our figure right there, it had, I believe, like the second highest first ionization energy, with only helium having it more. So even though hydrogen only has one proton, the fact that the electron is so close to the nucleus there, it's very difficult to remove it. It has a high ionization energy. It is not going to be characteristic of a low ionization energy like the atoms below it. It's going to be a non-metal. The metals that we would find, well, we saw that our alkaline and alkaline earth, as they become +1 and +2 cations, that's one region of the periodic table where we found them. We have our whole set of transition metals, and then we have metals that come after that. Aluminum is one more within our set right there. Very common sets of metals, all of these with low ionization energies. Now, when it comes to our nonmetals, we've seen that elements like oxygen and sulfur, those frequently become 2- anions when they're in ionic compounds. That was our understanding. I think it was back in chapter 2. But I would say tonight we just added something else. The second electron affinity, I said, is always unfavorable. If we're looking at a bare oxygen atom or a bare sulfur atom all by itself, it's energetically unfavorable to make it 2-. It involves adding a negative to something that's already negative. But somehow in these ionic compounds, it happens. So we're gonna have to learn a little bit more about that. Now, the end of the chapter, it has some tables like this where it shows different columns, like the alkalis or the alkaline earths, and it describes different properties. Let me show you a couple features that I think are important that I can connect to what we've been talking about. So first of all, when I look at those, when I think of something like the melting point or the density for these different atoms, that is not for a single atom. That is for a collection of atoms. When I talk about the melting point for magnesium, the atom of magnesium does not melt. Okay, it's not like a piece of chocolate or something. When you melt magnesium, it just becomes a pool of magnesium atoms. No, what we're doing is we're changing the relationship, right? From a solid to a liquid to a gas, we're changing the structure. So my point is melting point refers to a collection of atoms. The atom itself does not melt. Similarly, the density is referring to the arrangement for multiple atoms, not the density of a single magnesium atom. Now, if I look within these features for the alkalis, these are some of the lowest ionization energies. The alkalis are, the first column, are excellent metals. It's quite easy to remove an electron and make them cations. If I look within this one, when I'm thinking about the metals right here, there are bonds when I'm thinking about sodium solid, potassium solid, calcium solid. It's a different type of bonding than we've talked about so far. It's called metallic bonding. The types of bonding we talked about so far are covalent bonding and ionic. Well, we haven't really talked about the bonding as much as we've named them differently. We're going to see that you can have different types of bonding for our covalent molecules, different types when they're ionic. We're going to talk about that this evening. And then also within the metals themselves. When I look at the, excuse me, the right-hand side of the periodic table, let me add a few details for the different columns that we have here. So first of all, within this one, we've seen that oxygen in its elemental form is an O2 molecule. If you recall, sulfur, I said in its elemental form was S8. That's a picture of it. Sulfur forms this ring, sort of looks like a crown. That's the elemental form for sulfur. When I look over here with the halogens, I'm thinking now as far as when a melting point within this, these are molecules, F2 molecules, C2 molecules, Br2 molecules. When a molecular substance like this melts, we're separating those molecules. We're not breaking bonds within the molecule itself. The bonds are not broken when we go from a solid to a liquid to a gas. We're just changing the arrangement of those molecules. This systematic difference right here, that's something that we're going to go on to explain more in chapter 11. Last thought within here, at the bottom of my noble gases, there's examples here with like xenon and radon. Here's a picture of a molecule involving xenon. This is a pretty funky one. And you might think, well, you don't really have too many bonds with noble gases. Do they really form molecules? This actually is a molecule, the xenon tetrafluoride. That's something that we're going to look at more closely in chapter 9. So that's my real quick take here for the end of chapter 7. When it comes to chapter 7, I looked at some end of chapter problems pertinent to what we were talking about. So when I looked at the top textbook, these are a few that I thought were representative. This first one, write equations that describe the first, second, and third ionization energies for an aluminum atom. Which process for the ionization would require the least amount of energy? I thought this is a good open-ended question that touches on what we talked about tonight. Here's a second version of it where now, and when I say second version, this is now involved, you're recognizing the appropriate reactions for what would correspond to the first ionization of oxygen, the second, or the electron affinity. So this is in the learning objective of being able to recognize ionization energy reactions and electron affinity ones. This one right here is asking you to look to the periodic table and make predictions for the first ionization energy. That's something we practiced a little bit, where we're thinking about it in terms of size. And I would say we'd want to be able to extend that and not just think about the first ionization energy, but also do comparisons with the second or third successive ionization energies as well. This bottom picture right here, this is the same image that I shown. This is the successive ionization energy for carbon. We want to be able to understand the successive ionization energy as well. Understand why is it going up? Why is there a large increase? given a figure like this, be able to determine what element is it for. I've seen exam questions like that as well. So all of these are representative ones from the end of chapter 7. Now, to sort of take this and connect this back to some of the polling questions that we had right at the start, I got a new thing that I want to propose for you all, okay? I looked at how people were using the practice test leading up to the second midterm. And I thought people were making some really good choices. I was seeing a lot of students use a practice midterm and then follow up and try to improve their understanding. Either returning to the e-text, looking at the provided videos. I saw a lot of really good things taking place as far as learning in the days leading up to the exam. And you know what? I looked ahead and there's information as far as how you can prepare for the next midterm. And when I say there's information, if you click on the preparation for midterm 3, there's a study guide that they already have posted. There's a study guide that already has an outline of the learning objectives. It also includes some cool supplemental information that we're going to get to. This is later on in chapter 9. But my point is, in order to improve and get ready, we already have a roadmap provided for us for chapter 7. If we look within that study guide, there's already a breakdown on what the different exam questions will address, what the objectives are. There's already links to supporting videos where we can learn more. So as I look at this being a resource, it occurs to me, I can support your use of these resources. You do not need to wait until just a few days before the exam to become a pro on chapter 7. And in fact, you shouldn't wait. I think now is the time to become a pro on chapter 7. When I had that earlier questions at the start of tonight, as far as optimizing your time, studying smarter, perhaps not even studying more, I think a key thing would be to change your allocation of time a little bit. I think you're trying to learn too much the last week before the test. I think you're trying to learn too much about the preceding chapters. I think you're able to make some progress, but it would be better to have mastered it before you get to the final days. And I think I can help you with that. So what I'm going to do, I'm going to send you some information tomorrow. What I'm going to send out are going to be different exam version questions that are based on these chapter 7 of learning objectives. And I think that can help put you on a path to mastery for that. It's going to be optional. You can use it if you want, but I just saw so many good practices of people trying questions, seeing which ones they could or could not answer, and then following up and seeking to improve by either returning to the e-text or checking out videos. So I want to make it so that you can do that and you don't have to wait till the end closer to the exam. Okay, so that's my proposal. That's what I'm planning to do. Tell me here within the chat, are there aspects of that that you want me to modify? My plan is I'm going to send out some representative questions tomorrow, give you sort of a roadmap for how to use this. What suggestions do you have for me? Is there something that I'm missing within that? I think it's a pretty good plan, but you know, you're the user. I'm seeing a couple comments pertaining to aspects of the feedback within that. I'll see what I can do within that. I would say aspects on feedback for any of those. I know that's an important part of your learning. It becomes more and more difficult when we're sort of in this remote zone right here. And when I say remote right here, it's a little difficult to us necessarily be in the same spot at the same time. But that doesn't mean we can't still share ideas. So one aspect of that, I'll try to give sort of a good feedback when I'm posing questions within that, but we might have to work and brainstorm a little bit the best ways for us to share information with each other. Definitely sharing through emails, that would be one option. This is sort of a new idea for me. I'll put something together, I'll share it tomorrow, and then next class, next Tuesday, give me feedback on it. Let me know what you think within that, and we'll see how we can support each other within that. My main thought within here is, I think we need to take these ideas in chapters 7, 8, and 9, and we need to look at them in smaller bites. I think we can't have them be too large and then try to bring them all together at the end. I'm seeing some good suggestions, good comments within the chat. I'll read them all afterwards, and I'll see what I can do. Now, I'd like to take a little time here and now take those same ideas that we just saw at the end of chapter 7, things like ionization energy and electron affinity, and I want to connect that with ideas here that we have within chapter 8. Chapter 8 is about two aspects of bonding: ionic bonding and then covalent bonding, which would be taking place when we have molecules. Ionic bonding is a great match for what we've just been talking about, because we've just been talking about ions, the energy that it takes to make cations, the energy that it takes to make anions. So let's see how those now show up with this idea of ionic bonding. Now, on the periodic table, let's say we had an ionic compound with magnesium and oxygen, magnesium oxide. We've learned that if it's magnesium and oxygen, we don't need to include subscripts or anything like that, because we know the magnesium becomes +2, the oxygen becomes 2-. Magnesium oxide, MgO. Let's now connect that. What does it mean to say we made magnesium +2 and oxygen 2-? How does that connect with the ideas that we had back in chapter 7 that we just discussed? That's what I want to try to connect now. It's going to involve aspects of ionization energy and electron affinity. And we're going to first think about it in terms of the properties of these single atoms of magnesium, single atoms of oxygen. So when I think about electron affinity, I can remove one electron from magnesium. That's going to be endothermic. I can remove a second one. It's even more endothermic. Successive ionization energies always go up. The atom is getting smaller when it becomes +1, then +2. So as it gets smaller, it takes more energy to remove the electron. And then I see that it is really difficult to remove the third one. And we explain that because now, in order to remove the third electron from magnesium, we're removing it from an electron that's much closer to the nucleus. It has a much larger effective nuclear charge on it. That is not going to readily happen. Very difficult. It takes energy to become +2, but not nearly as much energy as it would take to become +3. Now, when it comes to the oxygen, it's favorable to add one electron. That's exothermic. I'm adding an electron to an orbital that has a large effective nuclear charge acting on it. But to add to a second one, that's back to being unfavorable. I'm adding a negative charge to something that's already negative. So if I were to sort of stop my story right here, we have an issue, because I've just said it is endothermic to become +2 for the cation. And it's unfavorable to become 2- for the anion. But then we also just said, this is what happens. Magnesium oxide, it does become +2 and -2. So we've got to look big picture a little bit more as far as what's going on. Simply looking at these single atoms and the energetics doesn't seem to cut it. So how do we explain the fact that it does become +2 and 2-? That's going to involve here this idea of ionic bonding. So the big idea within this section in 8.2 is that the energetics leading to the formation of these ionic compounds, it's going to involve getting to the cations, getting to the anions, and then having these cations and anions coming together. There's a few different skills within this. There's this topic of what's called lattice energy and the topic of what's called the Born-Haber cycle. In the pre-class video, I introduced a little bit the Born-Haber cycle. Let's talk about that one tonight, and we'll leave the lattice energy for next class. So this idea right here, let's say I'm making sodium chloride, and I have a transfer of an electron to make a sodium plus and a chloride minus. I don't want to think about these as isolated atoms. In the ionic compound, I want to think about this whole collection of anions and cations together. Because when we had an ionic compound, remember, we said we do not have a discrete molecule. We have this extended one throughout. And that's what's taking place when we have an ionic compound, when an ionic compound is being formed. So let's see how we get the energetics leading to this overall lattice being formed. So the way that I tried to explain it within the pre-class video, I said, okay, if we're forming sodium chloride, what would be the standard enthalpy of formation for that? We saw that we write a standard enthalpy of formation by thinking about the elements in their standard state. Sodium and chlorine gas combining to form this ionic compound. A piece of sodium being added to chlorine gas. We have the transfer of the electrons taking place, and this is a very exothermic process. You see like a fireball during this. So I would give a negative sign to designate this being an exothermic process. That's for the overall energetics. Within the Born-Haber cycle, we try to understand the different steps that would be involved, at least theoretically, in this process. What's leading to this overall exothermic reaction? If we start with the elemental form, the metal and the gas in this case, and we end up having the ions combined to form the ionic compounds, how can we begin to understand that energetically? That's what the Born-Haber cycle is about. So within here, we're starting with sodium solid and chlorine gas. We're somehow going to take it to the corresponding ions, and the ions then come together to form the ionic solid. What needs to happen along the way? So I list here different steps that need to happen. If we're starting with sodium solid and we want to end up with sodium ions, if we're starting with CO2 gas and we want to end up with the chloride ions, what needs to happen along the way? So what I'd like us to be able to do within this, I think we can assign whether these are endothermic or exothermic processes. Something that I had folks predict within the pre-class, and people were doing quite well at that. So let's see if we can understand the steps involved and whether they're endothermic or exothermic. This first one, I see a phase change. I'm going from a solid to a gas. That's endothermic. I see the ionization energy. Ionization energy is always endothermic, always takes energy. Breaking a bond, always endothermic. It always takes energy to break a bond. The only exothermic step I have in there is the fact that halogens have a favorable electron affinity, an exothermic electron affinity. So I think within this group, I think we're in pretty good shape of being able to predict all of these values. Those are all then represented in this overall scheme right here, where it's describing the energetics. This overall scheme here, this is what's called the Born-Haber cycle. It's really an application of Hess's law. It's showing the entire set of steps that would be involved. The learning objective on this is you're being asked to be able to identify or even write the Born-Haber cycle for any ionic compound and use provided data to calculate one of the steps, which is called the lattice energy. Now, when I say identify or write, I'm going to include a couple examples to show you how that typically shows up on an exam. So to talk you through the different steps right here, this one right here, we said that all of the enthalpies of formation, well, I don't know if we said it, all of the enthalpies of formation here for ionic compounds, they're always exothermic. It's always exothermic going from, in this case, like the metal and the gas to form the ionic compound. Now, as far as the process of how did that take place, we could conceptualize it this way. We could start with the sodium solid in the CO2 gas, and we could take it from the solid for the sodium, and we could turn it into the gas. We said that was an endothermic step. That's what that first arrow up is corresponding to. It's going from one plateau to the next. This one right here, this is breaking the bond in the CO2 to get Cl atoms. That was also endothermic. This one right here, this was the ionization energy. It's going from sodium gas to sodium plus gas and an electron. That's the ionization energy. The reason that we had to take it from the solid to the gas is that's how we define the ionization energy. Now, once we have this, we're going to add the electron onto the chlorine. That's the electron affinity. So as far as the different steps that are involved here, notice we had a couple ideas that we just saw in chapter 7. We just saw the ionization energy. We just saw the electron affinity. The other things that we added to it, we had a phase change and we broke a bond. The key thing is we can now use those values to get a missing value, this formation of the lattice. The coming together of all of those cations and anions that are these bare ions all by themselves, all of these separate ions coming together, moving to a lower potential energy in this extended solid, that's corresponding to the formation of the lattice. Now, the lattice energy is technically defined this way. You start with the ionic compound and you add enough energy to blast it apart into all of the cations and anions. That's going to be extremely endothermic. You've got all of them stuck together initially, and you're somehow going to add enough energy to break them all apart and into all of their corresponding ions. I mean, I've got a lot of fancy equipment in my lab. I've got high temperature furnaces. I don't even know if I have something that can do that. It's going to take a lot of energy to separate your ionic solid like that. Now, we think about it, the ions, though, coming all together. If you got all of those ions coming together, that must be extremely exothermic. The formation of that extended lattice, that 3D arrangement of cations and anions, all of that coming together, that is very exothermic. And in fact, that is the crucial step to understand conceptually the formation of ionic compounds. If we started with the sodium solid and CO2 gas, and we said, tell me about the energy that it takes to turn them into ions, it's much higher than it started. It is only the formation of that lattice that makes it exothermic. That's our key conceptual idea here. Now, some of the arrows are pointing up, some are pointing down. That is just how they're defined within this process. For me, what is important is the magnitude, to see how I go from one level to the next. Now, when I say you can write the Born-Haber cycle for any ionic compound, let me just talk you through this example right here. This one's very similar, but it's forming the ionic compound, this copper oxide. So we have what would be the elements in their standard state on the step above it. We've got quite a few different things that we could fill in. Let me just talk you through what would be involved in that process. I know that we have to take the copper solid and make it copper gas. I know we have to break the bond in O2, so we just have O2 atoms. I want to ionize and make the copper +1. I want to ionize and make the copper +2 because it's +2 within the ionic compound. Now, it's favorable to add one electron to the oxygen, but we said it's unfavorable to add the second. Notice how this is connecting back to the description that we just had in chapter 7 of the different parts. The first ionization energy, the second ionization energy. The first electron affinity, the second electron affinity. Now, if we were to stop right now, we are at a much higher potential energy than we started. The key thing is we got this huge formation of the lattice once again. It is that formation of the lattice that makes the entire process exothermic. And we can use these values to come up with what the lattice energy is. We can calculate the lattice energy. Now, I described this a little bit in the video and there are some questions about it, so let me give it a try another way. All of these have a value corresponding to what that segment, the magnitude of the segment is. 155, 339, 249, 745. Each of those is telling me the enthalpy change for that segment. I'm trying to find this missing one way over here on the right-hand side. Now, the reason these have signs on them, positive or negative, it's just telling me how it corresponds to the arrow as written. The way that I solve for this, the easiest way for me is, I'm just going to say, if I need to get that missing arrow on the right-hand side, I'm going to start from the bottom right here. And I'm just going to track through and say, how much energy will it take for me to get all the way up here? If I start at the bottom, how much energy would it take for me to follow through the track and get all the way up here? Because then that missing step, it will be that amount. Enthalpy, state function, pathway doesn't matter. So as long as I can figure out what does it mean to get to the top of the hill right here, I can use that to get this missing value. So what would it mean to take to get all the way to the top of the hill? Follow through with me. If I'm at the bottom right here, it takes 155 kilojoules to go up this step. The negative sign is, well, maybe you want to go down that step. I don't want to go down the step. I want to start at the bottom and say, how much does it take to go up that step? 155. And then another 339, another 249, another 745, another 1960. That gets me to the top of this hill right here. Now, I get some of it back with this value, minus 141, but then I got to go back up again with 790. All I'm doing is tracking through from the bottom as I snake through the cycle. How much energy does it take to reach the very top right here? That's what I'm doing with these different segments. And then boom, that would be the final segment that I have right there. The exothermic coming together of the lattice. This is using provided standard enthalpy. This is using provided data within the Born-Haber cycle to get the missing value. Now, as I've introduced this and tried to connect it here with chapter 7, let me give you a couple representative ways that I've seen this asked on exams. So first of all, here's some end of chapter questions. This first one, it says, list the individual steps that you would use if you're making barium iodide. Which of the steps would you expect to be exothermic? I think that is a really good question right there. I don't think you need to know what the particular values are in order to be able to think about the steps that are involved. If you can do that question right there, I think you've got a really good understanding of the ideas that are included in the Born-Haber cycle. This next question, 8.29, says, use some actual numbers. Use some actual numbers to come up with the lattice energy. You would not be asked, of course, to memorize these values. These would be provided ones. But this is one example where you're using provided data. I think both of these show up on the kinds of exam questions I see on this topic. So one format I see is experimental data is given and you solve for the missing segment, which is usually the lattice energy. That would be really similar to this question right here. You've got provided data all the way through, but it doesn't show you the missing segment right here. That's one exam format question, one format I've seen for Born-Haber cycle questions. Another one would be something like this. We don't ask you to like write out what the Born-Haber cycle is. So we usually would ask you a feature of it. So we might ask you to identify steps that would be included or not included. So take a second, read this one. In the Born-Haber cycle for sodium chloride, which of these steps would be included? Only one of these is correct. So see if you can identify both what is correct and why the other ones are incorrect. I see a lot of equations that are involving sodium and chloride. I see electrons listed in different ways. I think this is the only one that's included. A step of going from sodium solid to sodium gas, that is part of the Born-Haber cycle. This first one, why is that incorrect? It seems to be describing ionization energy, but it's with solids instead of gases. That's not how it's defined. The second one right here of somehow taking Cl minus and removing an electron from it to form Cl, well, that's not included at all. We want to get to Cl minus, we don't want to somehow remove an electron from it. This idea of taking sodium solid and separating it into the corresponding gases, that's not a step either. So this format right here, being able to identify steps that are not included in it, I've seen that as a question. I've also seen it like this, connecting the steps and thinking about whether they're endothermic or exothermic. format like this. Which of these steps is, for involving oxygen, is or are exothermic in the Born-Haber cycle? So it's asking you, is this, it would be worded to say, is this in the Born-Haber cycle? Is it being correctly identified as being endothermic or exothermic? So as I look within these, I think only that second one. I think it's going to take energy to break the bond in O2. It's an endothermic process. I think it's exothermic, adding an electron onto oxygen. It would be unfavorable to add the second electron on it, but it's favorable to add the first one. So I thought people had some really good questions within perusal about what are we supposed to write it? What are we supposed to do? These are, I think, the 3 ways that we ask it on exams. Use provided data to get a missing segment, know what the steps are and therefore be able to identify if one that's given is appropriate or not, and then also connect it as far as whether it's endothermic or exothermic. Now, within this one, we've spent some time here within chapter 7. I've looked at one aspect of the ionic bonding, in particular, spending time with the Born-Haber cycle. What we're going to do next time is we're going to look at, well, really, what contributes to the magnitude of the lattice energy? How can we understand that? How can we make predictions involving lattice energy? And we're going to be able to do that for sure. And then from that, we're going to extend to a different type of bonding, which involves our covalent bonding and what are called drawing and interpreting Lewis symbols. These ideas that we are picking up on Lewis symbols, that's going to be really important in chapter 9 too. It's going to extend over and we'll go from one to the other. Okay. So that's all I got for you this evening. As always, I really appreciate your attention and I'll be hanging around if you got questions for me.
Hi, Dr. Clark. I had one question.
Mhm.
If we go back to the slide with the properties of alkaline metals.
Okay.
I was wondering what could explain the decreasing trend of the ionization energies as you move down the column for group 1 metals. Is it because as you go down the column, the principal quantum number increases and the influence of the nucleus is weaker?
I think that's an outstanding explanation.
Okay.
I think that I think it's all about charge and distance, and they are in larger principal quantum number atomic orbitals. They're further away, so it's easier to remove them. Yep, I completely agree.
Thank you.
Could you briefly explain what we need to know about these other properties and how they relate to the ionization energy again?
Yeah, you know, I tried to connect just a little bit about how some of this data fits with other ideas that we were looking at in chapter 7. The end of that chapter, the end of chapter 7, has a lot of what's in the category of descriptive chemistry.
Mm-hmm.
They want to tell you about, oh, these are features of the alkalis. These are features of the noble gases. It sort of wants to just have some, well, it's called descriptive chemistry. They're giving you descriptions of those.
Mm-hmm.
In some ways, I find that a little unsatisfying because I think the start of the chapter is so greatly set up to give us explanations. And then I don't want to just have descriptions. I mean, just descriptions, that's like biology. You know, that's, I don't want biology. I'm not dissing biology, but I like it where we can seek to explain things. So I think within here, let's see what aspects of the descriptive chemistry we might need to be responsible for. For the most part, chapter 7 is from that first portion, much less involving the descriptive stuff at the end.
Okay. Oh, and then for the lattice energy, is that's just for 1 mole of the ionic compound?
Yep, correct. So that would be all of the ones within that aspect of the Bornhaber. When we're looking at the little bit more closely at the units, all of the different values they have listed within a table like this, like, let me get to it. All of these are in kilojoules per mole. And so that would be for the formation of the lattice as well. So in a sense, you're starting at the bottom and you say, okay, I got I'm interested in 1 mole of this ionic compound. Let's look at the energy for all the different steps along the way.
Okay, and for these Born-Haber cycles,
Yeah.
they're always going to be, like, if the standard state of one of the reactants is not gaseous, is it always going to need to become a gas?
Yeah, good question. So the kinds of things that we might have combined, if we think about our metals, there's pretty much always going to be a solid that we need to turn into the gas, right? Because almost everything on the left-hand side of the periodic table there, those are all solids. So whether we're looking at alkaline earth, transition metals, we're going to have to take those and turn them into a solid. If we're thinking about the things that then become our anions, those are going to be our nonmetals, right-hand side of the periodic table. We see examples of where they might be diatomic gases that we have to turn into atoms by themselves. They could be things that are diatomic that they're not gases. Like if we go further down the periodic table, chlorine and fluorine are both gases, but below that, when we get to bromine and iodine, we've got a liquid and a solid. So we would have to get those to be gases as well. I haven't seen it, but as I'm talking about it, if we had the anion coming from sulfur, we would have had to start with it in its elemental form, which would be that sulfur 8 molecule, and we'd have to take that and turn that into a gas too. Because our ionization energy and electron affinity are both defined in terms of interactions involving the gases. So we have to get them into gaseous atoms before we include that step. Okay.
And then just out of curiosity, on the chart for ionization energy, it's like a 3D chart. How come astatane isn't on there?
Was that when we were doing size, or what was that?
It was ionization energy removing electrons is the title of the slide.
Okay. So it's a 3D chart within here?
Yeah, it's slide 9 or 10.
Okay, let me see. Oh, this one right here?
Yeah.
And you're asking why is it lacking for us?
Yeah.
Yeah, it's good. I don't know. What are your thoughts?
I don't know, maybe we just don't know the ionization energy or something.
Yeah, it must be. I think if they had it, I think whoever the graphic artist was, it was probably nagging at them, right? It's a good question. What means when you can't get a ionization energy? There's this website I like. It's called Web Elements, and you can get the properties for like. You put in a given element, and it lists all the different properties: successive ionization energy, electron affinity, all of the stuff within there. So now you've got me tempted. I should look in there, the Web Elements, and see.
Yeah.
So, Joe, if you're still here, you take the makeup exam, correct?
That's right, yeah.
When is that?
It's Monday.
Okay, got it. What if you had your choice and I know you don't have a choice, would you rather take it the same week? Or do you like, or like the whole, how you're like a whole Monday off?
I like it better to take the makeup because it gives you a larger time frame to take it.
Would you like it though, like on, would you like it like on Thursday or Friday the same week, or not necessarily?
Um, I think yeah, Thursday or Friday would probably be better.
Yeah.
Just 'cause
Yeah, I don't know.
less
You know, if I'm
time.
a student, I don't know, because I feel like I'm sort of in the zone as the class is getting all set for it, and then we
Mhm.
continue on a little bit. So if it was
Yeah,
me, I'd probably like it, you know, a couple days later maybe, but a week later is stretching on a little bit in my view.
yeah, yeah. I just looked it up here. The ionization energy is on here is on this website for the.
Interesting.
All right, I'll see you later.
Okay. Hey, Nina, are you there? I got a question for you.